Hello again, Physics 1 students. In this video, I'd like to go through a few examples using Newton's law of motion in its rotational form to solve problems. And in this video, I really want to focus on objects which are only rotating. In a later video, I'll talk about how do you combine objects which maybe rotate and move from side to side, more general motions. So we saw in its rotational form, Newton's second law is written out as torque equals I alpha, right? And the torque, I won't bother with a vector notation. If it's positive, that corresponds to a torque that makes things want to rotate counterclockwise, and if it's negative, it's a clockwise twist. So and to be honest, for me, it's easier just to look at it, the picture, and you kind of know what you're expecting. So here's an example of a scenario we might have, and the goal will be to find alpha. What is the angular acceleration of a point here? So I've got a disk, which I'll take to be solid. I've given it a mass and a radius, and I'm going to imagine that I've got various forces kind of pulling on it at different directions. And I'll go ahead and give you numbers here. This will be 40 newtons. We'll say this one is 30 newtons. Now, to analyze this problem, so this is clearly a rotational problem. So let's think about this. Normally, what would we do? So usually, let's list our steps typically. We would draw a free body diagram, and then where the object is just a dot. Just a dot. Then you would write down net force in the x, F net in the y, and then from those you would solve for the acceleration in the x and y direction. That'd kind of be a flow through problems in the past. Well, the flow is really going to be the same now, right? The equation is very analogous to F equals ma. The only thing that's different now is that I should have written this here, it's the net torque. So I need the free body diagram to contain enough information for me to reconstruct the individual torques, and then ultimately so I can add them to find the net torque. So that means the main thing that I can't really do anymore is collapse everything down to a point. I need to keep in the spatial geometry. So I'll just leave the object more or less as it is, and I will draw in the various moment arms of different shapes, or of different forces. And then so that's the first correction. We draw the free body diagram, that's the same. Find the net force in the x, net force in the y, and now we will typically also find the net torque. And that could have been a net torque in x, y, and z, but for our problems, it'll always be a rotation in the plane, in which case it's just a number. And then once we use that, have those three things, we can find the acceleration vector, and now we can also find alpha. But the flow of the problem is very much the same. Draw the free body diagram, identify the net force in the x and y, now the torque, and then solve for acceleration and alpha. So here's a scenario. We've got a wheel. I've gone ahead and marked a pivot point. So it's going to rotate about this point here in the center. And we've got, two strings pulling at different angles. I'm giving you various parameters. Let's go ahead and solve for alpha. Let's see how that works. So let's go ahead and draw a free body diagram. I'm going to go ahead and leave the object extended here. And, that's important. We want to mark the axis of rotation because that tells us how to define the various lever arms. So in the problem I gave you, they both are at a common distance of the radius. but you'd have to look at the picture to figure anything else out. And then we have this force of 40 newtons, and we had this force of 30 newtons. Now, in this problem, we're going to assume that it's pinned down, that there's no linear motion. So what that means is that there will be normal forces generated at the pivot or along the axle, which do whatever it takes to keep the center of mass fixed. So I'm not going to worry about finding the net force or the accelerations. I'm going to go directly to the torques. So to find the net torque, I have to remember my formula for torque. Torque equals R, well, okay, in general it's R cross F. Or it's easier just to write torque is RF sine theta for the magnitudes, and then just add plus or minus depending on whether it wants to rotate clockwise or counterclockwise. That, to be honest, that's the fastest way. And I can think about this furthermore as R times F perpendicular. So I have two forces here. I want to find the net torque. So the net torque is going to be the torque of the 40 Newton force, and then plus the torque of the 30 Newton force. For these forces, I'm going to apply this R perpendicular idea. So this angle is 45 degrees. And if I wanted to know what is the component of the 40 Newton force, which is perpendicular to the radius, I would use cosine of 45. So I could write this as R times 40 newtons times the cosine of 45 degrees. And now what about the minus sign or positive sign? Well, I just look at it and I see that this force makes the wheel want to spin in a clockwise fashion. So that's actually going to be a negative torque. A lot of times you don't have to go back to this formal level to work out the cross product. You can just look at it and piece it together much faster from the diagram. What about the 30 Newton force? Well, it makes things want to rotate in a counterclockwise fashion. So that's going to be a positive torque. And it is already perpendicular to the lever arm. So I can just write that as R times 30 newtons. And there's no angle there. Or if I wanted to, I'd say the sine of 90, which is 1. The radius is a known quantity. It is 0.1 meters. So I can just type these numbers in, and I find 1 times 40 times cosine 45. I find up here, this is going to be negative 2.8 Newton meters. And over here, I'm going to get I'm just going to get 3 Newton meters. And therefore, the net torque, well, I just add those up and it becomes positive. So it's going to want to rotate counterclockwise, ultimately, 0.2 Newton meters. Okay, so that's my net torque. The net torque is it wants to rotate counterclockwise. So even though this force was larger in magnitude, because only the perpendicular part gives rise to a torque, it actually is smaller from a torque perspective than the 30 Newton force. All right, so that's the net torque. What about the moment of, but to find alpha, I have to remember that torque net equals I times alpha. And this is a solid disk, so I for the equals 1/2 the mass times r squared. And the mass I said was 1 kilogram. So this is just going to be 0.5 times 0.1 squared equals 0.005 kilogram meters squared. So I find the net torque was 0.2 Newton meters equals I times alpha, 0.005 kilogram meters squared times alpha. Therefore, alpha equals 0.2 divided by 0.005 is 40. If we keep track of the units on this, remember, a Newton is a kilogram meter per second squared. So this becomes, when you work it all out, 40 inverse seconds squared. And that's typically what happens for rotational things. And I like to slip in just a radian label. And that just reminds me that as I'm talking about radians per second, or sorry, I'm talking about rotational things. Ultimately, radians are just a placeholder. There are no real units there. I just put it there because it makes me feel more comfortable. And there you go. That's how you use Newton's second law for rotations to solve for the motion of something. Let's do another example. The example I want to do is a hammer falling. Okay, so I want to have a hammer and I want it to fall. And I'm going to imagine that there's a pivot point right here. It's going to fall under its own weight. So, and we're just going to let it free fall. So the first question is, how does gravity work for extended objects? Now, it's one of these things where I kind of went back and forth. Should I derive all these things or should I just tell you the upshot? And I think at this point in the semester, I'm just going to give you the upshot of how it works. You could go through and apply Newton's law of gravitation to every little chunk and add up all the effects. But the upshot is this. In an extended object, the effects of gravity the effects of gravity may be accounted for by assuming that it applies only at the center of mass. So the effects of gravity are as if they only applied at the center of mass. Okay, I don't want to, I'm not going to derive that. That's the upshot. And I mean all the effects. So that means for torque purposes, but it also means for potential energy points of perspective or questions. The potential energy changes will follow the changes in the center of mass position. So when you have extended objects, the influence of gravity can be kind of modeled as if it just applies at the center of the object. All right. So in this case, I'm going to give you some numbers here for this hammer. We're going to find the center of gravity and then we will find the angular acceleration of the hammer as it falls. So let's assume the hammer is built out of a rod. Let's say this has a mass of 2 kilograms. It's a heavy one. And then we'll assume that there's a big lump of metal on the end. So this will have a mass of, I don't know, 5 kilograms. That's a big hammer. Jeez. And we'll go ahead and let this thing have a length of, I don't know, let's just pretend it is 1/4 of a meter. So what we're really going to do is break this into two things. We're going to pretend that it is a point mass on the end of a rod with the appropriate units. And just for specificity, we will assume that the initial angle is 45 degrees. All right. First thing we have to do is find the center of mass position. So where could that be? Well, if I have a rod, its center mass is here at the center. So that would be at, well, if the whole thing is 1/4, that would be at 1/8 of a meter. And then the center of mass of this point mass on the end, that's going to be at a position of 1/4 of a meter. So in terms of like along the body of the handle or of the hammer, I mark 0 here at the beginning. I would say the center of mass position would be 1/8 of a meter times 2 kilograms plus 1/4 of a meter times 5 kilograms and we need to divide by the total mass, which would be 7 kilograms. And when you go through all this, you get a number which, if I've typed it all in right, I get 0.214 meters, which makes sense because it should be closer out to the end of the hammer rather than the center of the handle. Okay, so that's the center of mass position along the handle. Okay, so let's redraw this. I have my hammer, but the center of mass is actually right here. And the center of mass is at a distance of 0.214 meters. So we found the center of mass. And remember, the rule is that the effects of gravity are concentrated at the center of mass. Sometimes write COM. So that means we can just pretend that the entire force of gravity applies right here at the center mass. The force of gravity, of course, is just going to be the total mass times G, and minus because it's going down. All right. Having gone through all that, we can find alpha. So the goal is to find the torque due to gravity and set that equal to I. So we'll have to solve for I, the moment of inertia, and times alpha. So the torque due to gravity, well, I can see that the gravity makes it want to rotate in a clockwise fashion, so the torque is going to be negative. So the torque due to gravity will be negative, and I only want the perpendicular part of the force. So, and I told you that this was at 45 degrees, so that means the perpendicular component is going to be mg sine 45. So I'm going to get a lever arm of 0.214 meters times m times g times the sine of 45. And if I plug in numbers here, remember the total mass was 7. So that's just going to give me 0.214 times 7 times 9.81 times the sine of 45. And that gives me a torque of 10.4 Newton meters. Okay, so we've handled the torque part of this. To solve for alpha, we need to know the moment of inertia as it rotates about this point. So let's find that next. Okay, so I have a pivot point, and I have point mass on the end of a rod. Well, so I is going to look like since they're both rotating about a common axis, I can think of that as I of the rod about its end plus the moment of inertia of a point mass. So that's simply going to be 1/3 mass of the rod times the length of the rod squared plus the point mass. So that's just going to be mass of the point times the length of the rod squared. So plugging in numbers here, this is 1/3 times 2 times 1/4 squared plus 5 times 1/4 squared. So that's 1 divided by 3 times 2 times 0.25 squared plus 5 times 0.25 squared. And I get moment of inertia to be 0.6875, and it would be kilogram meters squared. So now we know the moment of inertia, and we can solve for the angular acceleration. The angular acceleration is simply going to be the net torque divided by I, and so that's going to be 10.4 divided by 0.6875, and I get alpha to be 15.13 radians per second squared. Okay, so those are some good examples. The first example is really simple, just where they're really just two forces, add them up, but you just follow the standard kind of flow. You find the net torque, figure out the moment of inertia, and then use torque equals I alpha to solve for alpha. When it comes time to handle gravity, really in all ways, from this point of view, you can you can just pretend that the force of gravity, the effects of gravity, are all concentrated right at the center of mass. In fact, oftentimes the center of mass is called the center of gravity for that reason. I want to point out something. So point something out. If you have some object and you have some pivot point, and there's a force applied at that pivot point. right at the place that the place that you're the axis of rotation, or however you want to say it. Well, in that case, the lever arm or the moment arm is 0, in which case the torque, which is R cross F, is 0. So when you apply the force, at the place where the force is applied, no torque is generated. You only get torque if you apply the force away from the axis of rotation. One really useful I don't know, corollary of this is that if you have the center of mass, well, remember what I said, gravity acts at the center of mass for an object, and we see that gravity generates no torque about the center of mass. So that's really useful. So if you are studying an object, if you sometimes you have a choice about what you want to consider to be the axis of rotation, and if you choose it to be the center of mass, then for the purposes of calculating the net torque, you can just ignore gravity. So that's a handy little fact that can help you. All right, so I've done a few examples calculating angular acceleration from net torques. We're going to, next up, we're going to use all of these things and try to solve for the motion of an object as it falls while tied to a pulley. Until next time, see ya.